In this video, we continue our journey of scratch building a first-person controller for VR in Godot. If you don't want to build all this yourself, have a look at our XR Tools plugin. Before we begin, the XR community is organizing their 4th Godot XR Game Jam. From the 8th of September, participants have a week to put together an XR game or experience made with the Godot engine. Follow the link in the description to find out more or join in with the fun. Last video we concentrated on applying the user's physical movements to VR. This is where VR is at its strongest, and we can see this in many successful games that limit itself to this. However, this constrains the player to the physical space available, and in many VR use cases, this is not enough. The user will have a need to move around the virtual world without physically moving. This, however, is where we encounter one of VR's weaknesses, as any such movement can lead to motion sickness. In this video, we'll look at implementing virtual movement. In order to move our player with input from our controller, we need to obtain this input. Godot has an input system geared to keyboard, mouse and joysticks. However, this does not fit the OpenXR's action map system well, regardless of the similarities between these. Godot therefore implements the OpenXR action map system closely, and lets us configure this in the OpenXR Action Map tab. Godot provides an action map by default, however, I've set up a custom action map with just the actions we require for our project. The actions form a contract between our game and OpenXR as to what inputs and outputs we require, regardless of the actual hardware the user is using and what buttons they are pressing. The other tabs allow us to configure our actual controller bindings. We always need to configure our simple controller, even though it is inadequate for most XR games. However, every runtime supports it, so it gives you the option to fall back and do something sensible. Next is the profile for our touch controller. This is the profile that will be used by my headset. According to OpenXR, you should only include profiles for hardware you've actually tested your game on, and rely on runtimes for other hardware to mimic one of the profiles you provide. You can thus not assume that if the touch profile is used, that the user is actually using a touch controller. However, many runtimes forgo this logic and will always fall back on the simple controller profile if no match is found. In practice, you have very little choice but to configure the different interaction profiles for each platform you're planning to release your game on. Finally, these bindings are loaded at startup and are immutable once your game runs. For many experienced game developers, this would seem to be a big shortcoming. To work around this, we often see developers create an action map that binds all inputs to matching actions, and then bind the OpenXR actions to the actual game actions so they have control over these bindings. Indeed, the default action map Godot provides is well suited for this approach. However, I'm not a fan of this approach. The player using their own hands provides a natural enough interface that when embraced by the developer solves many use cases. For example, if you allow a user to pick up objects with either hand, left-handed people can naturally interact with the game. Virtual movement, however, is one of the types of features where not being able to rebind inputs requires us to get a little creative. In our previous video, we put all our physical movement logic in a script on the XR Origin 3D node. For our virtual movement, we are going to start by adding a script to our character body 3D node. Godot handily creates a default character body implementation for us, and this will work great. This script introduces a few constants that allow us to control the movement. The movement logic itself is in the physics process. It first applies gravity if our player isn't on a floor. We then check if we initiate a jump. Next, we get a vector for our movement input. This is then used to calculate a movement vector that updates our velocity. And we use move and slide to move our character. With this logic, we can move our character using the keyboard, and can configure it to work with a normal joystick as well. We can keep this logic intact if we want to combine traditional input with XR input. So let's add our XR logic into this script. We start by adding an export variable so we can bring our XR controller into our script. After getting our normal input, we'll check if we have an XR controller. And if so, we use getVector2 to obtain the value of our movement action. Just as a reminder, we are using the name of the action from our action map here. The Y input of this is, however, inverted, so we simply multiply this with a vector to flip the direction. To make this work, we need to go back to our scene tree and link up our export variable to the actual controller we use for input. For the demo here, I'm using the right-hand controller, but you could easily enhance this to give the user choice between the left and right controller by simply changing this property. Now I can move myself around the scene by using the joystick on my right touch controller. We're moving fairly fast, but we can tweak our speed constant to improve this. Note also that I cannot move through objects. I'm properly colliding with those. This is a perfectly suitable setup, and you can continue down this route and add further movement code into this script. I prefer to split this logic up, but it is very much personal preference. We'll continue down that path. I will remove the non-XR input to keep things clear. However, this can easily be incorporated in the new approach. I'm removing everything from this script except the gravity logic and the move and slide function. We'll be manipulating the velocity from other scripts. We'll create a folder that will house these scripts, and create a script for our direct movement logic. We change this to a Node3D node, and we give it a class name. We'll be adding the script as a child to the controller from which we take the input. In our script, we'll need access to this controller, so we add a variable for this. We also need access to the character body node that we will be controlling. Next, we create an enterTree function to obtain these. This ensures our logic is rerun if we reparent this node. We're going to loop down through our parents to find these nodes. Note that typing this as Node3D is a mistake which we'll correct later on. If the node we're checking is the first XR controller 3D node we encounter, we set that. Same with the first character body 3D node. Finally, we get the parent of our parent to move down the tree. Now we can add a script to our right-hand controller. Our actual movement code needs to happen in our physics process. We do first check if we have a controller and character body. If not, we exit. We want our speed to be configurable, so we won't use constants here. And we want to allow for a different stray speed. So we add a maximum speed property as a vector too. Just like before, we'll get our movement vector from our controller as input. In our previous script, we simply used the transform of the character body, which assumes the character body doesn't have a parent and is always horizontal. Here we're adding a bit more complexity to handle more situations, and for that we start by deconstructing our current velocity for each of our character body's axes. We do this by projecting our velocity along each axis of our character body's global bases. Next, we calculate our desired forward and sideways movement using our input vector. Finally, we construct our new velocity by taking our current vertical velocity and then lerping the forward and sideways velocities to our desired velocities. The lerp ensures we have a smooth transition to the new velocity. This is again a choice that may not be valid for your use case. Before we can try this out, we need to change our mistake in enterTree and change the parent variable type to node. Now we can see that we can move around nicely. We do see that the effect of our lerp is a little strong, so let's improve that. We'll add an export variable to control our lerp. And we multiply that with our delta to apply it. Now that we have linear movement implemented, let's add in the ability to turn. We'll create a new script for this. Let's give that a class name and change the type to Node3D. We'll copy over the initialization code from our direct movement script. And we also copy the start of our physics process. We're only interested in the x value of our input, so we change our code slightly. Let's create an export variable for our turn speed and define this as degrees per second. I am making a mistake here in using degrees as radians. We'll correct this later on. Note that I had to make our input negative off camera, else we turn in the wrong direction. To implement our turn, we want to create a new basis value for our character body. I realize I never explained this, but a basis is a 3x3 matrix, a data type that holds the orientation of our object. We get the basis from our transform, so we have our orientation in local space. Note that for movement, we were working in global or world space. Now we rotate this around the basis's y component, using our input times our turn speed times delta. And we assign our new basis to our character body. We now need to add our turn function as a child node to our left-hand controller. As you can see, we can now rotate our player and fully move around our space using the controllers. Rotating like this specifically, and to a lesser extent strafing, causes motion sickness in a lot of players, especially those new to VR. Forward and backwards movement generally is alright for most players. Designing your levels to minimize the need for users to use virtual rotation is the best but often unpractical solution. Another option is to allow for teleportation, which we'll handle in a separate video. We'll look at two commonly used features to combat motion sickness. It is advisable to make this configurable to your users. Some may want this, some will want to disable it. The first is called step turning. What we've implemented so far is called smooth turning. With step turning, we turn in increments with a pause in between. We add a new export variable where we specify the degrees for each turn. Note that I'm again getting the degrees as radians wrong. We'll fix that soon. We're going to accumulate our rotation, so for this we define a new variable. Now we'll add how much we're rotating to this variable, and use our rotation variable to rotate. We add an if statement to ensure that we only trigger our rotation when our accumulated value is larger than our step value. As we've applied our accumulated rotation, we can now set it to 0. Now it's time to fix up our hints. We should have used radians as degrees. This keyword means that the user can set the rotation in degrees in the property inspector, but we're actually storing radians, which is what we're using behind the scenes. We do need to specify our default values correctly. For our turn speed, we'll set it to 45 degrees per second. We'll also allow a larger range. And we set our snap angle to 10 degrees. Testing this, we can see that when I physically move, everything is smooth as it should be. But when I use my controller input, we turn in 10 degrees increments. The second option we'll look at is implementing a vignette that blocks out peripheral vision as we turn using our controller input. We start by adding a new node to our XR camera node and renaming that to vignette. We then save that as a new effect scene. We add a Mesh Instance 3D node to our vignette scene. We're going to create a mesh for this in code. So we add a script to our node and add a function to update our mesh. We'll call this from our ready function. We start by defining a variable for our vertices and a variable for our indices. We'll define a variable that indicates how many steps we take to generate our mesh. This defines the number of segments for our vignette shape. Now we can resize our arrays to fit the data we're about to set. Now we loop through our steps. We calculate the vertex for this step by rotating a right vector so that we create vertices in a 306-degree circle. Now we add two vertices, one for our inner circle and one for our outer circle with a radius of 2. We will add two triangles to our indices array. Each triangle has 3 indices. So we start with an offset by multiplying our index by 6. We calculate a second offset, one index further but wrapped to our step size. And we calculate our indices for our two triangles. Note the typo at the end. We'll fix that in a minute. Now we create a new array mesh. We need to define a new array and resize this. And set our vertices array in the right entry and our indices array in the right entry. Now we can use this array to add a surface to our array mesh and set this mesh to our mesh instance. We change this to a tool script so our mesh creation code will run in our editor, and we fix our typo. When we reopen our scene, we can see we've created a circle with a hole in it. Our mesh is saved with our scene, so we can comment out the code in our ready function. We keep it in case we want to modify it later. We need to add a shader material to our mesh, and we add a new shader to this material. We want to be able to set the radius of our inner circle of our vignette. We add a uniform so we can set this radius. We also define a varying float called dist. A varying variable allows us to output data from our vertex shader. Our fragment shader will have this as an input that is interpolated. In our vertex function, we start with a vector by taking the x and y of our vertex. We calculate our distance as the length of this vector. For vertices of our inner circle, dist will now be 1. For vertices of our outer circle, dist will now be 2. We only want to change our inner circle, so we check if our distance is smaller than 1.5. This is safer than checking for exactly 1, as floating point errors may cause issues. Now we adjust our distance and our vertex to our radius. When rendering stereoscopically, our eye may not be centered on the viewport, so we use our projection matrix to project a distant point to obtain this center, and then offset our vertex by this center. Now we can update our vertex so we can see if our code works so far. Changing our radius on our material now changes the radius of our inner circle. For testing, I'm going to set this value to 0.5. We're going to output a projected value, and for that we need to know our z output. This bit of code will give us the correct near-plane value based on whether we're using reverse z. And we calculate our projection output by taking our vertex, z value, and 1 for our w component. Our output disappears due to culling, so let's set our render mode and disable culling. We can now see that our vignette becomes full screen. We also want to set unshaded, and we want to ignore our depth test. Now when we test, we can see our vignette working properly. We'll add a uniform to control the color of our vignette and default it to black. In our fragment shader, we can apply this to our albedo output. We also want to implement a fade, so we add a uniform variable to control that. And we modify our alpha output based on this. And we can see a nice fade. Back in our vignette script, we can now expose this. We add an export variable for our radius and implement a setter function. If we are inside our tree, we call a function that updates our vignette. We also call this update function from our ready function. Before I forget, we also set the render priority of our vignette so it's rendered early. We also want to mark the material local to scene. In our update function, we first obtain our shader material. If successful, we set our radius shader parameter. We multiply with the square root of 2 so that an input radius of 1 results in our vignette being just off screen. You can see that in action here. As we move to a value of 1, the vignette goes off screen. We can thus adjust our range. And we can make sure our mesh instance is only visible if our radius is less than 1. We also want to control the fade. So we add an export variable with a setter function as well. We call an update function if we're inside of the tree. And call this update function from our ready function as well. We can copy our code from our radius update and alter it for our fade. And we can see that we can manipulate our fade. Finally, we give our vignette script a class name. In our turn function script, we define an export variable that identifies the vignette to use. And in our process function, we can set the radius on our vignette based on our controller input. And we add an export variable so we can control our vignette strength. Now we can assign our vignette to our turn function node. One last thing that we need to tweak is move our mesh instance of our vignette a little forward so it doesn't get culled by our frustum culling. Now we can see that when we physically move, nothing happens. But when we turn with our controller, our vignette becomes active. With all this implemented, we can discover a new issue we need to solve. In the last video, we made logic so the player can move forward even when obstructed, so they can bend over an object. However, this means we can also put our head through a wall. We are going to solve this by querying our physics engine directly. We'll be implementing this on the script on our XR-Origin 3D node and adjusting our existing fade logic. We start by creating an export variable to define the size of our head. We also need an export variable to set the height of our head. In order to query the physics engine, we need a query object. We're going to cache one, so we define a variable for this. Now we can populate this in our ready function. We copy the code where we exit if we're in the editor or if we do not have a character body. Now we create a new shape query object. We copy the collision mask of our character body onto our query object. And we make sure we exclude our character body from the objects we collide with. We create a sphere shape to check collision width and set the size of this to our head radius. And assign this shape to our shape query. To implement our fade, we need to get the space our character body is a part of. And with that, we can obtain our space's direct state. We now build a transform to get our starting position for our head. We need this in global space, so we multiply our character body's global transform with a vector determining our head height. We set this as the transform of our shape query. Now we set the motion of our shape query to the difference of our current camera position and our starting position. Now we call cast motion on our direct state object to test for collisions, and check if we're colliding along the path by seeing if we have a result and if we are able to do our full movement. Now we set our fade to 1 if we're colliding. And now we can see that when we bend over the table, we don't fade to black until we're very far over it, giving us the ability to pick things up from the table. However, if we try to move through the wall, we immediately fade to black. And that is all we have time for today. In the next video, we're going to look at some tracking space issues and how to deal with recentering our position. Subscribe to my channel if you wish to be notified when it comes out. If you found this video useful, please give it a like. Thank you to all my patrons and members for your continued support. See you next time.